Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video, we are going to be discussing fluid at rest part 2. Remember in our previous video, we discussed about fluid at rest and I said we are going to be dividing it into 2 parts. So in the previous video, we did part 1. So today we are going to be dealing with part 2. So relax, do not go anywhere, I'll be right back. Welcome back to my school YouTube channel. In today's video, we'll be dealing with fluid at rest part 2. So before we begin with our lesson, let's quickly go through the objective for today's lesson. Okay, for the objective 1, define pressure and state its unit. 2, state the conditions for pressure in liquids. 3, describe an experiment to show that liquid pressure depends on depth. 4, state the application of liquid pressure. 5, solve problems involving pressure exerted by solids on surfaces and in liquid. 6, state Pascal's law and its application. 7, solve problems involving force, pressure and area in the hydraulic press. And 8, define atmospheric pressure and state its application. So let's begin with the lesson proper. So in the first slide, we are going to be looking at the meaning of pressure. Okay, so we simply define pressure as the force acting on an object per unit area perpendicular to the surface of the object. So the word perpendicular here simply means at right angle. So mathematically, of course, this is derived from the definition above. So mathematically, pressure P is equals to force F over area A. Okay, mathematically, pressure is equals to force over area. Right, and it is a scalar quantity. Now, when we say scalar quantity, it simply means that it has magnitude, but it does not have direction. So pressure is a scalar quantity, and it is also a derived quantity. Okay, and the SI unit of pressure is the Pascal, and this Pascal is also equal to 1 Newton per square meter. Okay, so other units of pressures are atmosphere. Okay, often represented or denoted by ATM. Then we also have millimeter of mercury, denoted by mmHg. Okay, from the definition above, when force is constant, okay, pressure is inversely proportional to area. So what that means is that as pressure is increasing, area is decreasing, or as area is increasing, pressure is decreasing. So at constant area, then pressure is directly proportional to force, meaning that as force is increasing, pressure is also increasing. So if force is decreasing, pressure too will also decrease. So below are an example for us to put this formula into work to show you how you can apply them in solving simple problem. Okay, so let's begin with example 1. A force of 10,000 Newton is applied to an area of 2 meters square. Calculate the pressure exerted on the area. Okay, so for this problem, I think we are not going to move over to the board because we are going to solve it. It's quite easy. Now we know that pressure is equals to force over area, right? And in this question, we are told that force is equals to 10,000 Newton and area is equals to 2 meters square. So knowing fully well that pressure is equals to force over area, so we just substitute the values that are given to us. So for the force, we have 10,000, while for area, we have 2. So if we divide this will be equals to 5,000 Pascal. Okay, 5,000 Pascal or Newton meter square, right? So the force exerted on the area is equals to 5,000 Pascal or Newton meter square. Okay, so the Pascal is denoted by PA. Okay, let's move to the next slide. So on the next slide, we also have another example, okay, just to drive home how to apply this formula. So example 2, a block of wood of mass 120 gram measures 30 centimeter by 6 centimeter by 5 centimeter. Calculate 1, the greatest pressure. 2, the least pressure exerted by the wood on a flat surface. And we are asked to take G, which is acceleration due to gravity, to be equals to 10 meter per second square. So for this problem, we are going to move over to the board to solve it. Okay, so solution. So first of all, let's write down the information, the parameters that are given to us according to the question. So we are told that mass is equals to 120 gram, right? And we are given the size of the block, okay, measures 30 centimeter by 6 centimeter by 5 centimeter. So first thing first, let's convert this to kg. Okay, so to convert this to kg, remember that 1 kg is equals to 1000 gram, right? So if you're having 120 gram and want to convert it to kg, so basically we are to divide the 120 by 1000. So let's do it here. Okay, so this is 120 and this is our 1000. So 0 will take out 0, right? So since we have two zeros here and there's an invisible point here, right? So we'll move that invisible point 2 times to our left. Okay, so we're having 1, 2. So that this is equals to 0.12 kg, right? So let's leave that. Now we have the first centimeter. Of course, remember that the block of wood is in the form of a cuboid. Okay, so we have the length, right? So this represents the length, while the second one represents the breadth, okay, which is 6 centimeter, while the third dimension, which represents the height, okay, which is 5 centimeter. Okay, so first of all, let's convert all this to meters, right? Now remember that 1 meter is equals to 100 centimeter, right? And we want to convert 30 centimeter to meters. So we write our 30 here. So from here, to convert 30 centimeter to meter, we have to divide by 100. Okay, so let's do the division here. 30 divided by 100, so 0 will take out 0. So at the end of the day, we'll be having 0.3, right? Now, for the second one, we'll be having 0.06 meters, okay? This is also meter. Why this will be having 0.05 meter, okay, which is 5 divided by 100, which is 1, 2, right? So these are decimal point. We fix a point, we fix a 0 there. We are asked to find the greatest pressure, okay, and also find the least pressure exerted by the wood on a flat surface. So in this case, we are going to obtain 3 areas. So from there we can get the largest area and also get the smallest or the least area. Okay, so the first one will be length. So the first area, let's call it A1. Okay, so that will be equals to length times breadth, right? So in that case, we're having 0.3 times 0.06. So if we multiply this, if we multiply 3 and 6, that will be equals to 18, right? But this is to 1 decimal place and this is to 2 decimal place. So we move the decimal point from here, we move it 3 times to our left. So that we'll be having 1, 2, 3, right? So at the end of the day, we are now having 0.018 meter square, right? And now having 0.018 meter square. So let's calculate for the second area. So let's call it A2. So the second area will be the combination of length and height, right? So that will be 0.3, okay, times 0.05. So this will be equals to 0.015 meter square. So just like what we did in the first one. So for the third one, let's call it A3. So that would be combination of the breadth and the height. That will be having base times height. So in this case, we'll be having 0.06 times 0.05. Right? So if we multiply this, that will be equals to 30. Right, and this is to 2 decimal place, this is to 2 decimal place, and there's an invisible decimal point here in front of every whole number. So we'll move 4 times inside or 4 times to our left. So we have 1, 2, 3, 4. Okay, so that this becomes 0.003 meter square. Right, so these are the areas. So from what you have done, you can see that the largest area is the first one, while the least area is the second one. So those are the ones that we are going to use in solving this problem. Remember that pressure is inversely proportional to force, right? Pressure is inversely proportional to force. So we are going to be having greatest pressure, okay, when the area is least, or we are going to be having smallest pressure when the area is largest. So in the first question, we are asked to calculate the greatest pressure. So greatest pressure, okay, greatest pressure will be equals to force over area. So we already know our force, okay. So let's calculate for our force because we've not gotten that. But remember that force, okay, force F is also equals to W, right, which is equals to mg. So in this case, we'll be having 0.12 times 10, right? 0.12 times 10 because we are asked to take G to be equals to 10. So if we multiply this, we'll be having 1.2, right? 1.2 Newton. So our force is equals to 1.2 Newton. So here we fix our 1.2 Newton, then divided by 0, okay? Since we are looking for the greatest pressure, so in that case, we take the smallest area, okay? So that would be 0.003, right? Now, 1.2 is the same as, say, 12 over 10, right? And 0.003 is the same as, say, 3 over 1,000, right? So let's put 3 over 1,000 here, right? So this is equals to 12 over 10 times 1,000 over 3, right? So, so 10 here is 1, 10 here is 100, so 3 here is 1, 3 here is 4. So that 4 times 100 will give us 400 Pascal, okay? So let's solve for the smallest pressure, right? Or the least pressure, which is 2, okay? So least pressure. So least pressure will be equals to force, okay? Least pressure equals to force all over area. So in this case, we are going to use the greatest or the largest area. So force remains 1.2 all over 1.2 all over 0.018. So if we divide this, we'll be having 66.67 approximately, okay? So 66.67 Pascal. Okay, so from the calculation, you can see that when the area is smallest, we actually obtain the greatest pressure. And when the area is largest, we obtain the least pressure. Okay, so this goes to tell us that pressure is inversely proportional to area. So let's return back to the screen to continue with our lesson. Okay, so we'll be talking about pressure in fluids. Okay, pressure in fluid. Now take note that the word pressure in fluid, we'll be using it interchangeably with liquid pressure, okay, or fluid pressure. They are the same. A liquid in a container exerts pressure at the bottom of the container. The pressure exerted has the following properties. Okay, 1, the pressure in the liquid is independent of the base area. 2, it increases with depth below each surface. 3, it increases with the density of the liquid. 4, at the same depth, the pressure is the same and acts equally in all directions. So let's move to the next slide. So on the next slide is just a little experiment to show us that pressure depends on depth. Okay, so apparatus, the things that you need for the experiment, we need a tall can, and that can was made of tin. Okay, then a small nail, running water from tap. So procedure, and the procedure is very easy. Okay, so A, make 3 small holes, A, B, and C of same diameter along a vertical line on one side of the can using a small nail. Then B, fill the tall can with water from tap up to the level above A, as you can see in the diagram below. Okay, as shown in the diagram below. Then C, observe the jets of water from the holes. Okay, so let's move to the next slide. Now, observation. A, water jets through the holes at different speeds. Okay, then B, the lower hole C throws water farthest and fastest, followed by B, and lastly hole A, Then C, the water leaves the hose at right angle to the wall of the container. And that is why when we're defining pressure, we added that it is perpendicular to the surface of the object. Okay, so this shows that pressure is perpendicular to the wall of the container. So what is now our conclusion? Now, pressure due to water at C is greatest and at hole A is the least. Therefore, pressure in liquid depends on depth. Okay, pressure in liquid depends on depth. Now, we also have another experiment to show us that pressure in a liquid is independent of area. Okay, when we're talking about pressure in liquid, the things you need to know about them, we said one of them is that pressure in liquid is independent of area. So in this experiment, you can use any shape of object. The shape can be cylinder, it can be cone, whatever. Okay, you are still going to obtain the same result. So, but in this case, we decide to use a cuboid. Okay, so we consider a liquid of mass m kg and density. Remember that this is the symbol of density and it's called rho. Okay, so density kilogram per meter cube filled in a container of base area A, as you can see from this diagram here, to a depth h. That h is in meters as shown in the diagram below. The liquid exert pressure on the bottom of the, let's move to the next slide. So the liquid exert pressure on the bottom of the container as a result of its weight. Okay, so from there, remember when we're discussing about density, we also made mention of something like this, that volume of the liquid is equals to volume of the container. And the reason is not far-fetched because a liquid does not have its own shape. Okay, it does not have a definite shape. So it actually depends on the container in which that liquid is found. Okay, so the volume of a liquid or the volume of the liquid is equals to the volume of the container, right? And that object there is a cuboid, and we know that the volume of a cuboid is equals to length times breadth times height, right? And remember that the length times breadth represent the base area. Okay, so that we're having base area times height, but the base area here is actually length times breadth. Okay, so mass of liquid is equals to, now remember that density is related to mass by density is equals to mass over volume. Okay, so that if we make mass the subject of formula, we'll be having that mass is equals to density times volume, right? So mass of liquid is equals to density times volume, okay, which is equals to base area, because we've made sure that the volume of the liquid is equals to the volume of the container, right? So the volume here is actually the volume of the liquid, right, which is equals to base area times height, okay, then times density represented by rho. Okay, so weight of liquid equals to mass times acceleration due to gravity. Okay, and we already know that our mass is equals to base area times height times density. So in place of mass here, we replace it with base area times height times density. Okay, so that we'll be having that the weight of the liquid is equals to base area times height times density times acceleration due to gravity. And remember that weight is also a form of force. In fact, weight is defined as the force acting on the body due to gravity, okay, or as a result of gravity or gravitational pull of the earth on an object. Okay, but remember that density is equals to force over area. And from here, we know that our force is equals to base area times height times density times acceleration due to gravity. So in place of force here, we replace it with base area times height times density times acceleration due to density divided by area. That is the formula for pressure, force over area. So divided by area. Now, since we have area here and there's an area here, so they will cancel out. So that at the end of the day, pressure is now equals to depth times density times acceleration due to gravity, which is h times rho times g. Okay, hence pressure in liquids is given by depth times density times acceleration due to gravity. And this experiment also shows that the pressure in a liquid is independent of the base area. Okay, so let's apply this new formula of pressure now in solving some problems. So let's take, for example, 1. What is the pressure on the bottom of a vessel when it is filled with a liquid of density 800 kilogram per meter cube to a depth of 2 meters and we are asked to take acceleration due to gravity to be equals to 10 meter per second square. Okay, so these are the parameters that are given to us in the question. H is equals to 2 meter, which actually represents depth, while G is equals to 10 meter per second square, which is our acceleration due to gravity, and rho is equals to 800 kilogram per meter cube, which represents our density. But our new formula for pressure is equals to depth times density times acceleration due to gravity. And these three parameters are given to us. So we can easily calculate for the pressure. Okay, so that pressure P is equals to the depth H times rho density times acceleration due to gravity. So that we'll be having 2 times 800 times 10, and that will amount to 16,000 Newton per second square, or you can say Pascal. Okay, that's still correct. If you use Pascal, if you use Newton per meter square, they are still correct. This is where we end the preview for today's video. So you can watch the complete video by clicking on the link in the description below, and this will take you to my school website. There you have to subscribe to enjoy the complete video. In the complete video, we solve more examples where we apply this formula in solving problems. Then we also talked about atmospheric pressure and its application, and we also talked about Pascal law and its application and more. I believe you enjoyed this video. If yes, please do not forget to hit the like button, click the subscribe button, and lastly tap on the notification bell to get informed as soon as we release the next videos.